Today we are talking about the topic of local stiffness matrix and global stiffness matrix. Now let us assume a single element let us assume a single spring element, and we have a one node and this is a second node. At the one node we have a displacement u1 and at the second node we have displacement of u2. Let us assume the force which is exists at the node 1 is f1 and the force exerted at the node of 2 is f2. So now there is some stiffness of the spring is k, that we are assuming as some stiffness of spring is k. Now so as we know that the force F is equal to k dot delta. Delta is known as the relative displacement of the node 1 and node 2 with respect to node 1 and node 2. So we are assuming here that u2 is greater than u1. So delta, relative displacement of delta is equal to u2 minus u1. So now put it here, the force F is equal to k dot u2 minus u1. Again, as we know that for the equilibrium conditions, force F1 plus force F2 should be 0. That means summation over F should be equal to 0. The total net force from 1 and 2 should be equal to 0. That is known as the equilibrium conditions. Now, again, we are using of this force in the node 1 and node 2. So here F1 is equal to minus of F2, and as we know that F is equal to k u2 minus u1, so F1 is equal to minus k u2 minus u1 and F2 is equal to k u2 minus u1. Here we are using of the F1 is equal to negative because F1 is equal to minus of F2, so F1 should be negative and F2 should be positive. So here we are using a F1 is negative and F2 should be positive. Now we are just converted into the matrix form. So F1 upon F2 is equal to we are just multiply insides, so we are getting is minus and minus, so that is a plus, so that is the k is positive, and this into this is minus k, this into this is minus k, this is k, and here is u1. This matrix is known as the load displacement matrix, and this stiffness matrix ke is equal to, that is k minus k minus k and k is known as local stiffness matrix. Why we are using a local stiffness matrix? Because we are using a single element, that's why we are saying a local stiffness matrix. If we have a number of 2 elements, 3 elements, then we are calculate the equivalent of the stiffness, then we are say it's a global stiffness matrix. So here we are using a local stiffness matrix of for the single element. Now, if we are using a two series like that, one spring, two spring is there, right? So at the node of first, displacement u1, at the node of 2, displacement u2, at the node of 3, displacement u3, and the force is F1, F2, F3. So here is the one element and this is the two element, that is K1, that is K2. So the stiffness matrix of first element, so K equivalent of first is, that is K1 minus K1 minus A1 and K1. For second stiffness matrix, K equivalent second is gives you the K2 minus K2, K2, K2. Now we are just adding here because as we know that this is the one node, this is second node, that is also one node, that is also second node, and this is represented of the second node, third node, second node and third node. So as we are seeing here, that means this node is known as 2 comma 2 and this node is also known as 2 comma 2. So this and this should be added at the when we are convert into the global stiffness matrix. So again we are using a global stiffness matrix, so load stiffness matrix. So as we know that if F1, F2, F3, that is equal to, first is K1 minus K1 minus K1, that is K1 plus K2, and again is minus K2 minus K2, K2 0 0, and that is U1 U2 U3. So we are using, this is a first node, second node, third node, and here is the first node, second node and third node. So first node, so here you are using that 2 node. So 2 node is there, 1 and then, so that is K1, K2 is added at the point of K1 here, that's why we are adding here. And this whole stiffness matrix K equivalent of the system, that is K1 minus K1, K1, K1 plus K2, 0 minus K2 and K2 is known as global stiffness matrix here. Thank you.